the first thing I need to do is finish off the end of last class. So last class we were talking about gradient descent, and I rushed through this stuff about smooth approximations. So the short version is that we wanted to use the absolute value loss because it helped us deal with outliers. It didn't give as big of a penalty when you had a very large residual or a point very far from your line. And absolute value seemed like a good choice, but it isn't smooth or differentiable at its center point. And we don't go in too much in this course into why that's a problem or all the ways of dealing with it. But roughly speaking, with gradient descent, we are looking for a point where the gradient is 0, and we're kind of expecting the gradient to get closer and closer to 0 as we get near the point. And that's just not true with the absolute value function. The gradient is just the same everywhere, and then suddenly you're at this point, and it's not even defined there. So some of our assumptions are violated, and that causes problems. And the strategy for dealing with that we take in this course is to say, instead of changing the optimization algorithm, which I would call step 3 from our 3 steps from last time, let's change the loss function, or step 2, to have the properties we want but also be smooth. And so that was the idea behind this Huber function. So up here, it's a piecewise function that's quadratic for part of it and absolute value for part of it. And I think it's easier to just look at it. So you can have variations on this, but roughly speaking, it's smooth in the middle where we don't really care that much anyways. It's linear far away, where that's where we are having problems with outliers. And this function is smooth, and we can take the derivative and do gradient descent with a constant step size, and everything kind of works out. Okay. Now, the log sum x stuff. So that is on your assignment. And the motivation for talking about this as it's presented here is that maybe you want to do a type of regression that's the opposite of robust regression, which we'll call brittle, that excessively tries to cater to outliers, or in other words, it tries to minimize the biggest residual. And so that's what the slide is saying. It's saying my loss or my score is the biggest distance, the max. Remember a few times ago we talked about the different ways we're using max. So here I'm using it in terms of the maximum of a set of things, where each item in the set is the residual for one data point. So we want to minimize the max, which can also be written as the infinity norm. So when we went from L2 to L1, we got more robust. If we go in the other direction and go all the way to the extreme, that's kind of the most unrobust. And the idea is that we can approximate this max with this log sum exp. And notice a couple of things. First of all, this is the first time that we're dealing with a loss that isn't just a sum of some function over all training examples. That's what you're used to. We define a penalty for a particular training example, and then our overall penalty is the sum of that thing over all the training examples. That's what we did for squared, L1, et cetera, et cetera. But here we're actually doing something different, which is taking the max, and that's, again, not smooth. And it's also not in this form that we're used to seeing things, but we're going to approximate it with this log sum x, which, among other things, well, it both makes it, deals with smoothness issues and puts it back in this form we're used to of having, of having a sum of things. So let me give you the intuition for why you can approximate the max of a bunch of numbers as this log sum x thing. exponential functions really amplify things. If I take e to the power of 1,000, that is a huge number. So if I have 10 numbers, I don't know, 1, 50, 200, 7, -10, some bunch of numbers, and I take x of all of them, it's going to really amplify things such that, well, 200 doesn't seem that much bigger than 100, but e to the 200 is way, way bigger than e to the 100. Like, so big that you could pretty much forget about e to the 100 because it's so incredibly tiny compared to e to the 200. So when we take x of all of our things, not exactly, but roughly, we now have a sum of these exponentiated numbers, and roughly only the biggest one really matters, especially if the numbers are nicely separated. And so we can approximate this by, we'll just ignore all the numbers except for the biggest one. And if we did that, the sum would instead just be the biggest one. And so we now have e to the biggest one. So I guess, I assume most of you know this, but for those who don't, exp is the same as e to the power of a number. And so I now have the biggest one, and then I take the log of it, and then I get back to the number itself. So this log sum exp chain of operations actually sort of pulls out the biggest number for us, but in a smooth way. It's not exactly the biggest number. And in particular, it's smooth in the sense that if I change any of the numbers a little bit, the output will change a little bit because they're all in there just a little bit. Whereas with max, if I have max of 2 numbers and I change the little one a little bit, nothing happens. In fact, nothing happens when I change the little one until it becomes the biggest one, and then something changes. So now that we've talked about gradient descent, we can start to think about smoothness in terms of gradients. And so the original max function only really has a gradient with respect to the one parameter corresponding maybe to the biggest number, or not exactly true. It's not an exact correspondence, but somehow a bunch of gradients aren't really there, and then suddenly they become the biggest, and they're suddenly there, and that's this thing of being not smooth. Any questions or comments on this? Okay, I guess, despite not liking to do demos without planning them in advance, let me just try something. Okay, so here's some numbers. Right. So you can see that this operation pretty much pulled out the max of those numbers, which in this case was 20. And we just talked about the intuition for it, but it becomes less, the approximation becomes less good if I have something very close, because then my whole argument was that you could just neglect all the other ones, but if the next biggest one is very close, you can't really quite neglect it, and so the approximation is not quite as good. Okay. So that was the last thing I wanted to say that I didn't have time to say last lecture, and we will return to this log sum x thing later in a few weeks when we talk about multi-class classification in a particular context. The way it's in your assignment is also in a different context than it's in here. The way it's in your assignment is that it's a way of approximating absolute value of x. Here we talked about the Huber function, which just smooths out the middle there. But we could also say absolute value of x is the same as the max of x and minus x. You think about that? So if you just plot the functions x and minus x, the max of the two in the other sense that we talked about the word max before, which is the maximum of two functions outputting a third function, is absolute value of x. And so you can just write absolute value of x in that way, and then use this log sum x thing to approximate the max of two quantities. And that's the way it's done in the assignment. Yeah, we have a lot of stuff to do today, so I'm going a bit faster than I like to. All right, on to today's topic, which is nonlinear regression. So last time we talked about gradient descent, and while we were talking about gradient descent, we talked about a whole bunch of things, including this squared error being sensitive to outliers. Talked about the absolute error, which solves that problem, the Huber being a smooth version of that, which accomplishes roughly the same thing that we want to accomplish. And then we talked just now about this L infinity norm, which does brittle regression, which is the opposite intuition. It only cares about the biggest distance, and so it's going to really be influenced by outliers. We talked about non-differentiability, and we talked about smoothing these things out, which is, again, not absolutely the only way of dealing with it, but it's the way we're going to do it in this course. Talked about gradient descent. Yeah, someone asked about this word stationary point. So stationary point, critical point, place where the gradient is 0. I'm using those interchangeably. When the function is convex, that's the thing we're looking for. When the function is not convex, you could have other ones that are not the global minimum. Okay, moving on. So we've been drawing these losses and starting to reason about, when we look at one of these pictures, is it going to be robust or not? And there's really many steps in the process. What's actually happening is, for each point, we're making a prediction, subtracting our prediction from the real thing. That's our residual. Then we're passing it through this function that we're drawing. Then we're summing it up for all examples. That makes up our loss function. Then we're minimizing that whole thing with respect to W, iteratively with gradient descent. So there's quite a lot of steps now, and I'm just throwing out this picture and hoping it'll make sense because we've been talking about it a lot. But you can be comforted by the fact that there's a lot going on here. Okay, so the absolute value is more robust in the sense that it doesn't grow huge when the residuals are huge. So we could go even more extreme. We could have functions that actually bend the other way. And they're kind of super robust in a sense. But the problem is that these functions are not convex, and they're much harder for us to minimize. And I'll show you a demo in a minute. Okay, so L1 might do something like this. Maybe not horrible. This very robust loss maybe does something like the green line, which you could be happier with or less happy with, depending on what you're trying to accomplish. But maybe it would always also do this red line for a certain initialization of our optimization algorithm, because now it's not convex. There could be local minima. Thinking about it, what does it mean for that to be a local minimum? It means if I jiggle that red line a little bit, it's worse. In any way I jiggle it, changing the slope or the intercept, so I'm just going to call it a day. But if I make a big change, I can actually find something better, and yet gradient descent is just a local optimization algorithm, and when it's locally happy, it's just going to stop. Okay, so we can say that the absolute value is the most robust that we can get while still being convex. As soon as we start to curl, then we lose convexity. So in that sense, the absolute values could be considered special. Any questions or comments on this? Ari.
Do we ever use non-convex functions and then add like randomness, like stochastic gradient search or something like that?
Okay, that was a loaded question. Do we ever use non-convex functions and then add randomness like stochastic gradient search? We'll talk about stochastic gradient later in the course. It is random, but not in the sense that you're getting at, I think. I mean, one way of dealing with local minima is that we can randomly restart our algorithm a whole bunch of times. It'll maybe fall into a different minimum each time, and we can take the best one. That does make sense, and it does involve randomness, but not in the same sense as stochastic gradient, which uses randomness in a very different way that we'll talk about later.
Okay, cool.
Okay. Fine. So getting to today's topic then. Oh, Ali.
Sorry, yeah, just a question about the saying that the absolute value is the most robust most robust convex one. Couldn't you make it like even lower slope to make it?
Okay, interesting question. So Ali is asking, I claimed this was the most robust convex loss, but couldn't you make the slope lower? So let me just make sure I'm right before I say this. Yeah, so that will not actually change anything. So making the slope lower is the same as multiplying the whole thing by a constant less than 1, like 0.5 times absolute value. And then you're doing that for every training example, and you're summing that up. So that's the same as multiplying the whole loss by 0.5. You will not actually get a different minimizer.
Okay.
But if you change the shape, then you do get a different minimizer. Okay, so the first thing I'll say is there's very much to be said about nonlinear regression, and we will not say that much of it in this course. And a lot of it is going to happen today. Also some later. We'll talk about neural networks and deep learning later in the course, and that will also be doing regression, and it'll also be nonlinear. But there is a whole bunch of regression algorithms that are kind of the regression cousins of the classification algorithms we talked about. So we had decision trees for classification. There are regression trees that are basically, you do a decision tree, but at each leaf you have a regression instead of a classification or something like that. There's KNN regression. So at each point, instead of looking at the k nearest neighbors and voting, you look at the k nearest neighbors and then you average the results, and that is going to be your prediction because they're numbers now. So there is a bunch of this stuff, and I just want to tell you that it exists and that we don't have time to really go into it because we cover so much in this course, and that you can check out the bonus slides if you want to see more about that. So instead, what we're going to do today is focus on a different way of getting nonlinear regression, which is building on linear regression and messing with it to make it nonlinear. So let me not spend too much of our valuable time convincing you that there are nonlinear things out there in the world. Yes, there are things that depend on other things in a way that is not linear. Here is a toy picture of that with just one feature and the y values looking sort of parabolic in terms of the feature. And if I tried to do linear least squares, I would get this, and maybe I could do L1 or whatever. It doesn't matter, and that's what we talked about last time. Step 1 is we were picking the model. Step 2, we were picking the loss. Step 3, we were picking the optimization algorithm. So once the model is linear, you can play with the loss however you want. You're never going to get a parabola. So here's what we're going to do. We're going to kind of hijack linear regression to fit a quadratic model for us by inventing a new feature that is x squared. And then we're going to say, let's just do regular linear regression. And that new feature gets its own coefficient because every feature gets its own coefficient. That's how linear regression works. And when you stare at this thing, it's like, wait, that is the specification of a parabola. For if I get to pick beta W1 and W2, I get to pick any parabola out there. So we can call this a change of basis or changing the features. So if I started first just in a one-dimensional case, say I started with only one feature, I had those 4 examples, then I can make this new thing. And we're going to use x in this course to mean the original data set and z to mean the transformed data set after I do this kind of stuff to it. So, hey, that column of 1s is great. It gave us the intercept from before. And now there's a connection. And that trick of adding a column of 1s sort of fits into this bigger framework here. We can keep our column of x, and we can have a new column of x squared. And we're also going to use the notation v in this course. When we switch from x to z, we will also switch from w to v. Just to get things more clear, because then d can still refer to the original number of dimensions, and v will be of some other size, like in this case 3, even though d equals 1. Okay, so we can just do the same old thing. However we were going to solve the problem, normal equations, gradient descent, whatever, it all works because we aren't actually changing the problem, we're just changing the data set. I mean, linear regression should work for any data set, right? So we're saying, instead of changing the algorithm, let's change the data set. And that kind of results in changing the algorithm, but what's so nice about it is we can use everything we already know. We already sat here for an hour talking about linear regression, another hour talking about normal equations. So let's use that 2 hours of work and put linear regression to work for us instead of coming up with some whole new thing. And that's exactly what we're doing here. Now this last line is probably where the most mistakes happen. When you're done, you have v, not w. V is a thing ready to make predictions on a thing with 3 features. So you cannot just give it x test equals 7. You have to give it a thing with 3 features. That's what it's expecting. So you must apply the same transformation to your test data. Go from x tilde, as we're calling it, our test data, to z tilde. And then we can use v to make those predictions. And in fact, it's a general principle. Whatever you do to your training data in training, you typically do those same steps to your test data before making a prediction. And actually, this notion of messing with the data instead of messing with the algorithm seems to come up in life sometimes, not just in this course. I don't know if this is a relevant example or a waste of time, but for example, we're scheduling TAs for these big courses in the department, and we have some system that optimizes based on people's availability and stuff, and someone comes to me and says, this person shouldn't be assigned to this because they're busy or they're the head TA or whatever. And I could go into the code and say, if name equals so-and-so, do this and that. But instead, I just say, go into their survey results and just change it to I'm busy, I'm busy, I'm busy. Run the code again, and you'll get what you want, right? It's sort of the same type of thing, where we just change the data to get the behavior we want. Maybe not that relevant. OK. Right, so we do this and it does the right stuff. And I'll show some demos soon. Okay, so this is the general form with degree p polynomial. We just now have p plus 1 features, assuming we just started with one feature for every degree of the polynomial, x squared, x cubed, etc. So there are some connections here if you've taken or are taking Computer Science 303. This may look to you like the van der Waals matrix. It is. This is a monomial basis, etc., etc. There are fancier ways of doing this, but for now it's fine. So one other thing is we've just kept talking about one feature. So what if you have more than one feature to start with, which is a very reasonable thing to happen? Then there's a whole bunch of terms we might need to worry about, like not just x first feature squared and second feature squared, but also the interactions like first feature multiplied by second feature. And you can imagine getting a lot of features when you do this. And we'll talk next week about how to deal with that. Okay. Here we go. Okay, so first I'm going to show some demo stuff relating to the loss function thing from before, brittle, outlier, this and that, and then I'll show some stuff relating to the polynomials that we just talked about. So here's a synthetic toy data set with some outliers like what we saw before. Here's some code that we don't need to look at. So what I'm plotting here is for each of the different losses, I'm plotting the thing on the left, which is the function, or how do I penalize different sizes of errors. The middle is the contour in parameter space. Last time we also talked about parameter space versus data space. On the right-hand side, we have the actual fit in data space. And I can rerun this. Can do it for absolute value and Huber. They look very similar. You can't even really see the curviness there, but if I set this to 1, you can see the Huber looking kind of how we talked about. And then we can talk about this super robust loss that does the square root, for example. And I didn't put any effort into optimization here. I'm just calling scipy.optimize.minimize without thinking whatsoever. And if I do that, crazy stuff happens. So here's an example where the star is the global minimum, the red star, and the cyan star, I'll make it a little bigger, is where it actually ends up. And then you can see that fit in the data space on the right. And it's sort of as advertised on the slides. And I can rerun it a bunch of times, and it'll be different every time because it's picking a random initialization for the gradient descent. But I also want to show you that I zoomed in here. So there's two things we could be worrying about here. We could be worrying about the non-smoothness, which is there, and the non-convexity. And so there's just a whole bunch of things that can go wrong here. It could get stuck in the local minimum here. I'm not even sure that's happening. The optimization may just be choking because of the non-smoothness. I'm not quite sure. But if I rerun it a bunch of times, I'll just get different results every time. That's the nature of dabbling in the dark arts of non-smooth, non-convex functions. Ali?
When you say the algorithm might be choking on because of the non-smoothness, you mean like it tries to differentiate at 0 or something?
Yeah, Ali asked what did I mean by the algorithm might be choking. So it has certain termination conditions when it's going to stop, looking at the size of the gradient, but possibly a whole bunch of other things. I don't know all the details of how the standard SciPy optimizer works, but it's observing something that's making it decide to stop, either because the gradient doesn't make sense, or it's small enough, or something. Yeah, I didn't look into it that much. Right, and then this is the brittle regression. So that's the infinity norm one. I smooth it with the log sum x. And you get this very interesting picture. So there's a lot of intuition to pull out of this. One is the picture on the right. You see, it's kind of the same distance from the upper points as the lower points because it's trying to minimize the worst distance. And what's very interesting is look at the middle curve. Look at the parameter space. See that curved contour or curved level set? The intuition there is if I make W a little bigger, I want to also make the intercept beta a little bit smaller. And just think about what that means now, going, as I was saying, from the data space to the parameter space. That means if I want to make the slope a bit bigger, I better move the whole thing down so that my predictions far on the right kind of stay the same, because I actually only care about my predictions far on the right. I only care about minimizing those big errors, and I completely don't really care what's going on the left, because those are small errors anyway. So we can actually interpret the slant of the loss in terms of the data space, which I think is very nice. Except we don't really have much time. Okay, polynomial features. So here is a made up, again, 1D data set parabola like we had in the slides. I've just randomly split it into some training points and some validation points. And now what I'm going to do is fit different degrees of polynomials and make this pretty picture, just showing the training points. So you may have seen something like this before, but okay, p equals 0 is just 0, p equals 1 is a line, 2 is a parabola, 3 is cubic, etc., etc. But the punchline here is that by the time I get to 7, crazy stuff is happening. And again, if you're taking 303 or some other course, you've experienced this. But we can really see it in the validation error. So the training error keeps going down. It's just like all the other stuff in the course. This p is a hyperparameter. It's controlling complexity. We can make training error get smaller and smaller. In this case, we can make it exactly 0 by setting it to n minus 1 or n plus 1 or whatever it is. But look at the validation error. It's doing that thing that we were kind of talking about for many weeks now. It's getting a little better, and then it's getting worse. It's getting worse because overfitting. And we can look at the overfitting. Yeah, good job, p equals 7. You got 0 training error. You passed through all the points, but at what cost, right? At this ridiculous thing. And so when I measure the validation error on those validation points, it's high. So here, everything's nice because it's a nice little demo, and you would select p equals 2 if you were just looking at validation error, but maybe it's not so easy always, and we'll talk about that as well. But great. Okay. So little time. Let me leave that because it's not absolutely and utterly essential, and we'll come back to it if I have time. Okay. Okay, so now that we can play this trick of transforming things, we can do it for all kinds of functions. It doesn't have to be polynomials. We can do whatever thing and then have that be a new feature. And that function now kind of joins our library of things we can use to make up our fit curve. So if your points look like this because you were measuring, I don't know, temperature over many years or whatever, then if you just tried to use a linear regression, it would be bad. If you tried to use polynomial, quadratic would be bad. If you tried to use 10th degree, it would be good for 3 years, and then it would go down to minus infinity, like below absolute 0, temperature for the month after my last measurement, which makes no sense. So maybe I want a different basis, and I can use, for example, a new feature that is sine x, and then I can actually fit this thing. So we're not just limited to polynomials. And maybe I have points that look like this. No problem. Remember, linear regression is just adding stuff up. So I can have a sine made-up feature, a cosine made-up feature, and a linear, well, that's the original feature, an untransformed one. And then I can also fit this. So what you might be thinking now is, this is great if I knew what basis I was supposed to use for whatever problem I had, but hey, it won't normally be one-dimensional. I can't just look at it and say, obviously sine, obviously polynomial, and things are always harder than they initially seem. So one possible approach to that is a particular non-parametric transformation, which we will now talk about. So we can think of linear regression with the polynomial basis as you have these basis functions like linear, quadratic, etc. And the thing I skipped earlier tries to give some intuition about that, and you might be interested in reading it. Okay, I said this, right? Basis might not be obvious. So imagine the whole non-parametric thing, well, we talked about k-nearest neighbors, for example. As we add more data, it kind of incorporates that more data, but we don't commit in advance to a level of complexity. So we can do the same kind of thing here, and a famous or popular version of this is called Gaussian RBFs, where RBF stands for radial basis function. And basically the idea is that the functions that we're adding up are little bumps centered around the training points. So this polynomial thing was global. It just says I have this much parabola, this much cubic, this much line, and I'm just adding them all up everywhere. Here the basis functions are local, saying I have a little bump around this training example, a little bump around this training example, and I'm going to add them up. And now that means I have one new feature per training example. So my z will actually be n by n. If I have n training examples, I'll have n features. And that's what makes it non-parametric. The complexity grows as I add more data. And it has some nice properties which we don't have time to talk about. So this is what it looks like. It looks like a bunch of Gaussian-ish bumps per point that I add them all together such that the sum of them is this nice smooth approximator of the whole surface. And as you get far away from the data, it just tapers off to 0. So there are some questions. I left some things unspecified. Well, I said this. I said we'll have n of them. I said they'll be centered at each training example. So the regression weights, the w's or the v's, I guess now, become the heights of these bumps. Because remember, it's each function times its personal coefficient plus next function times its coefficient. So the coefficients control the heights. And the width is a hyperparameter, which is the main thing I want to talk about. Okay. Great. This is what I wanted to show you. So I'm fitting the same data set with these Gaussian RBFs. And the sigma parameter controls the width of each bump. And when sigma is very small, like 10 to the minus 2, they're very narrow. So that makes sense that you can get, well, you can certainly get 0 training error. We'll just pretty much set each coefficient to be the value we saw there. And then we have this quite ridiculous looking fit for sigma equals 10 to the minus 2. So we have these very narrow peaks. Very narrow peaks means I observed this. That doesn't tell me anything about what's going on here. Not that far away. The width is like, how far away do I still believe I'm learning something from that nearby point? It's sort of like K and N-ish in that sense. So when it's very narrow, I saw something great. I believe in a tiny neighborhood around that point, it's sort of that value, and then I just drop off to 0, and I don't know anything because there's no point near me. And then that's what you're seeing with 10 to the minus 2. With 10 to the minus 1, the bumps are a little bit wider. Still doesn't look that great. But say with sigma equals 10, I'm not showing you the bumps, and maybe I should for a prettier picture. But you still have these bumps centered at each point, like in the top left, but they're very wide. So when you add them up, this bump over here is overlapping the next bump over here because they're so wide. So when you add them up, it's this nice, smooth curve. And so sigma is our hyperparameter controlling the complexity of this thing. So you might think, wow, n features, that's a lot of features. This is going to overfit like crazy. And it is going to overfit like crazy until we talk about regularization next week. But even for today, if we make sigma big enough, we can still make it underfit. But it's just we can't quite get that nice balance between overfitting and underfitting, which we'll get next week. But we can still control the complexity. But before with the polynomials, we were changing p, we were changing the number of features, and that's how we were controlling complexity. And here the interpretation is that we have n features no matter what, but we can still control complexity with this width. And so one way you could even define complexity if you wanted to, although it's not a perfect definition, is how fast do I allow my regression line to vary? Because if it can vary crazy fast, that's a very complex fit, small sigma. And if it has to be very smooth, that's sort of a simpler fit. Kevin?
Yeah. What about the weights now? Are they the same height as the data point? Because then
are the weights still the same height as the data point? No. I mean, I haven't printed them out or explicitly checked, but they shouldn't be because the thing you're looking at is the sum of all of those bumps. But even under a particular data point over here, probably all 7 bumps are contributing because they're wide enough that they haven't yet gone to 0 at some particular point. And so I would expect the v values to be smaller.
So there's some correlation between the weights depending on...
For sure. If you change sigma, you will get a different v, for sure. Liam?
I mean, like, the best graphs there kind of look like they could be made by a polynomial. I would only need, like...
Yeah, the best one could be made by a polynomial, but here's the beauty of it, Liam. You didn't have to decide that in advance, right? The polynomial one, you had to say p equals 2, and then it was great. But if you have some high-dimensional thing and you don't know what value to use, then things are a bit more complicated. And you could try validation, cross-validation, and that's all reasonable. But this is another approach where, OK, we still have to fiddle with sigma instead of fiddling with p, but you can get something that looks like a polynomial here. It's actually different because it'll eventually go back to 0 instead of just going up forever. But this is just a different approach. And again, we'll make it better next week. OK. Fine. This last plot is just calling a scikit-learn thing instead of calling my own code, and it's more for your reference later. And you can play around with the hyperparameters in scikit-learn, and you'll see that they basically correspond to our hyperparameters, but with different names. I guess usually I had you do that on the assignment. This assignment doesn't have you compare with scikit-learn, so if you're interested, you can look here. Have you? Ari.
Yeah. Is there a cost for? Because like if you pick polynomial, you're just matching that, right? And now we're matching like with a ton of different, because there's n now instead of 2 or 3 or whatever you pick. So is it much slower, or is it?
Yes, there is a cost. So let's go back to the slides. Okay. Well, I'll get to that if I can. Yeah. Okay. So this is a general form of what we were doing, which is I make n features. And mathematically, we can write them down as some function of the distance between that training point and my x. So if my training point is here, I have a decreasing function, then as I move away, I get these kind of bump shapes that I talked about. Personally, for me, it requires quite a lot of staring at a slide like this to really get it. So I was hoping maybe the demos were an easier starting point. Yeah, I would say stare at this offline for 20 minutes and then ask on Piazza afterwards, because there's too much going on here for it to be really doable at lecture pace. But here's something I do need to say. Very important thing. I just said when I make predictions, I need to do the same process on my test data as I did on my training data. So now, to make these n features on a test example, I have to compute the distances between my test vector and all my n training points. Which means, like k nearest neighbors, I have to keep around my training set, because they define the features. The features are based off of the training points. And so it's this, again, non-parametric, can't throw away the training data situation we had with k and n. And then to get to Ari's question, so yeah, we have this n dependence in our prediction speed. And there are clever ways of speeding it up that we'll talk about later in the course. Okay, this we already saw in the notebook. So again, like with polynomial, where you could have these features and other features, you could do that here. You could have RBF and linear, or RBF and an intercept. The Gaussian RBFs by themselves will go to 0 very far away from the data. I can throw in a linear feature, and then they'll be a line very far away from the data. So it's quite a powerful framework that we introduced today, where we can do all kinds of transformations, mix and match. And at the end of the day, we already know how to solve linear regression, which is normal equations or maybe gradient descent, depending on the situation, or maybe something else. Okay, so we talked about not talking about all of these methods and referred you to the bonus slides if you're interested in terms of trees and all that kind of stuff. We talked about nonlinear transforms, and in particular, we talked about polynomial and RBF. Earlier today, we also did the brittle regression stuff. And that's it for today. I would like to see questions on Piazza about today's lecture, because I really wanted to rush through it so you could do the assignment, but I know it was at a very fast pace, so please don't be shy, and have a good weekend.